I saw this X post from Terrible Maps and immediately thought, wow, what a great opportunity to do some math. We think of the sky as being above us. Where's the sky? Well, it's that blue thing up there. But when you think about it, really, most of the sky is below us. The sky, if we had to define it, is this layer of atmosphere that surrounds the Earth, and it doesn't just surround the Earth wherever you're standing, it surrounds the Earth, well, all around it. That's what we mean by surround. So most of the sky is actually beneath you. Or at least that's how it looks in the pictures. But can we run the numbers to confirm that indeed most of the sky is below us? And if so, just how much? Is it 20% above us, 80% below us? What are the percentages here? Well, we'll look at the math, and from now on, when you ask someone what's up and they say, the sky, you can say, pfft, hardly. We'll begin our calculations with the flat Earth case, just like we see in this picture, and then we'll move on to the three-dimensional case with spheres. For each case, there are two important measures of physical reality that we're going to need. Whether the Earth and its surrounding atmosphere is regarded as a circle or a sphere, they both have radii. Let's say that the radius of the Earth we're going to call r. And then a separate radius, which we are also going to need, is the radius, which is the distance from the center of the Earth all the way to the edge of the exosphere. The exosphere is the outermost layer of the atmosphere, which is what we'll regard as the sky. And we're going to call that larger radius S. So this is the radius of a circle whose circumference goes around the exosphere and whose center is the center of the Earth. We need to know what these numbers are for our calculations. The radius of the Earth is about 4,000 miles. There are various estimates for how far away from the Earth the edge of the exosphere is, but we're going to use the estimate of 62,000 miles. That's the distance from the Earth to the edge of the exosphere. Thus, this measure, this radius S, is 62,000 plus 4,000, so 66,000. So S equals 66,000 miles. All right, now that we have those numbers, we are ready to start doing some calculating. Let's first quickly address what the calculation method is going to be for the flat Earth scenario. And perhaps this is a good time to guess yourself. What percent of the sky do you think is above us compared to the percent that is below us? Keep in mind that this drawing is not at all to scale. All right, now for the calculation, we're going to have to figure out the area because we're working in 2 dimensions right now. We need to find the area of this sky, which is going to be the area of this blue circle minus the area of the Earth. The blue circle, keep in mind, is the one that has this as its radius. The blue circle has the center of the Earth as its center, and it goes all the way out to the edge of the exosphere. So we'll take that area and subtract the area of the Earth. That's going to give us the total area of the sky, this ring around the Earth. Now, the area specifically of the sky above us is a little bit more difficult. This shape is what's called a segment of a circle. I've drawn my own very rough sketch here, so here we are standing on the surface of the Earth. We can regard ourselves as just a single point. The rest of the objects are so large that our diminutive size is not really relevant to these calculations. So how do we find the area of this segment, the sky that's above us? Well, there is a well-known formula for just that. Consider the central angle, the angle that opens up from the center of this circle and cuts out that circular segment. This central angle has some measure. Let's call its angle measure theta. If theta is the measure of this angle that cuts this segment of the circle, then the area of the segment is given by this simple formula. 1/2 S squared, where S is the radius of this circle. I'm calling it S because, remember, that's what we've named the distance from the center of the Earth to the edge of the atmosphere. That's S. So S squared times theta minus sine of theta. So we know what s is. We already said that's 66,000. So we just need to figure out what theta is, this angle measure, and then we can calculate the area. How do we find theta? Well, all we need to do is use a little bit of trigonometry. Let's draw this segment, which comes from the center of the circle and is perpendicular to this line. Remember that this is the line passing through our point on the Earth. So this segment we've just drawn is perpendicular to that. That gives us these two congruent right triangles. We know they're congruent by angle, angle, side. Now, let me just draw this triangle separately so we can get a better look at it. So imagine we've just popped that right triangle out and enlarged it a little bit so it's easier to work with, and here it is. Certainly, the hypotenuse of this right triangle, of course, is the radius S. That's the distance from the center of the Earth to the edge of the atmosphere. Meanwhile, this distance, which is the height of the triangle, is actually just the radius of the Earth, which we've called r. Finally, this angle here, well, remember, this whole central angle was theta, but now it's been cut in half when we got these two triangles, so this angle actually has a measure of theta over 2. Now, sine of theta over 2, if you know your trigonometry, is the opposite side over the hypotenuse, SOHCAHTOA, sine opposite hypotenuse. But I don't know the length of this opposite side, so I'm going to use cosine, which is going to be the adjacent side over the hypotenuse. So cosine of theta over 2 is r over s, adjacent over hypotenuse. Why is this useful? Well, because remember, we're trying to figure out what theta is. Since I know cosine of theta over 2, what we can do is take the inverse cosine on both sides of this equation, and that's going to give us theta over 2, and then we can just double that to get theta. So in the end, theta is equal to, we took the inverse cosine of both sides, so inverse cosine of r over s. Again, that would have given us theta over 2 because it undoes the cosine function. We would then need to double it so that we're just left with theta. That is theta. And this is a number. It's not unknown. This is a number we could punch into a calculator because we know r and we know s. And because this gives us a number for theta, we can also plug that in here, and thus we'd be able to evaluate sine theta. In the end, if we run the numbers, we get that the area of the sky above us is about 6.3 billion miles squared. So that's the area of the sky above us. By the way, if you're curious where this area formula comes from for the segment of a circle, it comes from finding the area of this whole sector that's cut by that central angle, and then taking out the area of this triangle part. But alright, we've done the hard part. That's the area of the segment of sky above us. Now we need to compare that to the total area of the sky. Like we said, all we need to do to find the total area of the sky is find the area of the sky circle, so to speak, and subtract the area of the Earth. I'm sure you know the area of a circle, pi r squared. That sounds like area to me. So for the area of the sky circle, we're going to do pi s squared. Again, remember s is what we're using for the radius of the sky circle. So this is pi s squared. That's the area of the sky circle, and we subtract this inside area of the Earth circle that we don't want, and that's going to be pi r squared. Again, we know these numbers. S is 66,000, R is 4,000, so we can just punch this into a calculator, which gives us about 13.6 billion miles squared. That's compared to what we just calculated, 6.3 billion miles squared above us. So let's do the division here to figure out what percent of sky is above us. It's going to be 6.3, that's the sky above us, divided by 13.6, that's the sky total. Of course, they both had billions of miles squared, but that's why we don't have to write it, because they would just cancel out. And in total, this is about 46%. That would mean, of course, that 54% of the sky is below us. So is it true that most of the sky is actually beneath our feet? Yes, it would appear so, based on this flat Earth and flat sky model. But you may think this looks a little low. If we look at this picture, it appears that way more of the sky is below us than above us. but that's just because the scale here is completely deceiving. In the picture, the two circles looked something like this, so then we're comparing the area of this segment here to the rest of this area, and all of this looks like it would be quite a bit more than all of that. After all of this sky beneath us consists of the same amount as the sky above us, because we see that there on the opposite side, but plus all this stuff on the sides, which is a lot extra. But it's not actually a lot extra, because remember, the radius of the Earth is only about 4,000 miles, compared to that radius of 66,000 miles for the atmosphere. So an inaccurate, but more accurate diagram would look something like this. At which point we can draw those lines tangent to the Earth to cut the atmosphere circle into segments, and you can see that, yeah, 46% of the sky being above us, that does make sense. Because we have all of that sky above us, we have the same amount below us on the opposite side, plus what's actually just a little bit extra here, because the Earth is very small in comparison to the whole atmosphere. But okay, I know you sphere Earthers are probably getting a little impatient. How do we run the numbers, and what do they look like in the hypothetical situation where the Earth is a sphere? Well, let's say this black sphere that I'm sketching as best I can is the Earth. Let's imagine that this black sphere I'm sketching is the atmosphere, which means its radius is that number we've been calling S. That's 66,000 miles. Then, sharing this same center is another sphere, which is, of course, the Earth. And somewhere on this Earth, we stand happily looking up at that small little piece of sky above us. We then imagine a plane which touches the Earth right where we stand and cuts a part of the atmosphere off. Like, here's the atmosphere, here's that plane, and it leaves this little spherical cap on top. It might look something like this, and that is in fact what it's called. What we were calling a segment in the circle situation, segment actually means something different when we're talking about spheres. So this here that we're trying to find the volume of, the sky above us in the 3D situation, is actually called a spherical cap. Now the big ideas of this calculation are similar to before. To calculate the total amount of sky, we'll calculate the volume of the atmosphere, and then subtract the volume of the Earth that's inside. That will just leave us with the sky volume, and we want to compare to that the volume of the sky that is above us, but this is a fairly complicated shape because it's a spherical cap. How do we find the volume of something like that? Well, this spherical cap is part of the sphere, and just like the sphere, of course, all of its cross-sections are 2D circles. Of course, the area of each of those 2D circles is just pi times whatever the radius of the given circle is squared. For a comparable situation, think about a cylinder and how we would find the volume of that. So here's a sketch of a cylinder, right? It's a tube. Every cross-section of a cylinder is just a circle. Let's say the height of this cylinder is h, and we'll call the radius of the cylinder B. Then all we have to do to find the volume of a cylinder is essentially just add up the areas of all of those cross-sectional circles. The areas of all those cross-sectional circles are just pi times the radius squared, and we're calling the radius b, so pi times b squared, and we're stacking up all these infinitely many circles to get this cylinder. It has a height of h, so when we add up all of these circles, we're basically just scaling the area by that height of h to get a volume, and this is the volume of the cylinder. It's like taking the area of that flat circle and stretching it vertically by whatever the height is, in this case h. The calculation is very simple, but it's only so simple in this case because with a cylinder, all of the cross sections are exactly the same. Every circle here has a radius of b. With our spherical cap, of course, that's not the case. The radius of this first circle I've traced is fairly large, but as we go up the spherical cap, the radii get smaller. Now, to deal with changing quantities like this, we really need some calculus. I'm not going to go into all the nitty-gritty details of the calculus, but I am going to go into some detail. The first thing you have to imagine with me is that we've rotated the sphere, so our spherical cap looks like this, and I'm gonna kind of reconstruct it on a graph. So here's my XY plane. Now, one cool way to create a sphere is to rotate a semisphere about the x-axis. So here's my XY plane. Now, one cool way to create a sphere is to rotate a semicircle about the x-axis. If we took this semicircle and spun it around the x-axis, we would actually trace out a sphere. Now, let's suppose that this is a semicircle such that the sphere created when we rotate it about the x-axis, or revolve it about the x-axis, it creates the atmosphere. That means the radius of this semicircle has to be the radius of the atmosphere, which we've decided to call S. More specifically, because remember, just for this sketch, we've imagined that we've rotated the sphere. More specifically, it's this part that, when revolved about the x-axis, is going to be giving us our spherical cap that we're trying to find the volume of. So this is just that spherical cap sketched again, but on this graph. And of course, you can see the challenge here. The radius starts big, but it gets small. However, in each case, the radius of these circles, whose areas we need to calculate and then, in a sense, integrate together, these radii of the circles are just the heights of this semicircle function at the x-coordinates. What's this radius here? Well, it's just the height of the semicircle function. What's this radius here? It's the height of the semicircle function. With that in mind, it would be really useful to have a function for this semicircle. Hopefully, you remember the equation in general of a circle, which is x squared plus y squared equals the radius squared. To adjust things for our situation, there's a couple things we have to do. First, instead of x squared, we would have x minus s squared. That accounts for the fact that this circle isn't centered at the origin, here where the x and y axis meet. It is in fact centered over here. It's been shifted over a radius length, that's s. So it needs to be x minus s squared, not x squared. But besides that, it's just plus y squared, and then equals the radius squared. Again, we're calling the radius s. Now, this isn't a function, this is just an equation, which would give us the whole circle. To get a function, we're going to solve for y, and that would tell us the height at each point of the semicircle based on a given x-coordinate. So to get y by itself, we subtract x minus s squared from both sides, and then take a square root. Thus, we have that y is equal to the square root of s squared minus x minus s squared. Now remember, for any given cross-sectional circle here, this is the x-coordinate, the horizontal position, and the radius of the circle, which is the height of the semicircle function, that is y. That height there is y. So given an x-coordinate, what's the area of that cross-sectional circle? Well, it's pi times the radius squared, and the radius is the height of the semicircle, which we figured out is this. Thus, the area of each cross-sectional circle would be pi multiplied by this squared, because this is the radius. But if we square this, that's just going to get rid of the square root. So it's just pi times s squared minus x minus s squared. Remember, the radius needs to be squared, and we have squared it. That's why the square root is gone. So this is the area of each cross-sectional circle at a particular x-coordinate. And this is where we can't get further without calculus. Like I said earlier, we need to integrate all of these cross-sectional circles together to get the total volume of the spherical cap, which remember is the volume of sky above us. So, integral symbol. We need to integrate this with respect to x, where x goes from, we can say 0 here, out to wherever the spherical cap starts or stops, depending on your perspective. Now, this stopping point of the spherical cap is just wherever it touches the Earth. Now, as we said earlier, the outside of the exosphere is about 62,000 miles away from Earth. So this distance here from the edge of the exosphere to Earth, that's about 62,000 miles. So we need to integrate from 0 all the way up through 62,000 miles later. And remember, S is 66,000, that's the radius of the atmosphere. So we could plug that in here as well, but at this point it's just number crunching. This is a very easy integral for anyone who knows calculus. You would just use the power rule, and in the end, this comes out to about 547 trillion miles cubed. So all right, 547 T cubic miles. That's 547 trillion cubic miles. Okay, phew, that is most of the hard work. That's the volume of the sky that is above us. Now all we have to do is figure out how much sky there is total by calculating the volume of the atmosphere and subtracting the volume of the Earth. The volume of a sphere is 4/3 pi times the radius cubed. So for the atmosphere, that's going to be 4/3 pi times, we're calling the radius S cubed. Remember, S is about 66,000, so if you run the numbers on this, we get about 1.2 quadrillion cubic miles. But of course, we just want the volume of the sky, so this really shouldn't include the volume of the Earth that is within it, so we also need to subtract the volume of the Earth. The volume of the Earth is 4/3 times pi times the radius cubed. We've been saying that R is about 4,000 miles for the Earth, and this is about 268 billion cubic miles. This is, of course, an overestimate because we're using 4,000 miles as the radius, when in reality the radius is a bit less. So then the actual number we're looking for how much sky there is this minus that. And now at last, we can calculate the percent of the sky above us in the 3D model. The percent of sky above us is the amount of sky that is above us at any particular point, which we've calculated to be 547 trillion cubic miles, divided by the total amount of sky, which is this minus that. This is very small compared to that. Even after doing the subtraction, you get about 1.2 quadrillion cubic miles. Since both of these numbers are in cubic miles, we can cancel the units out, and what we end up with is a percent, and that is about 45%. So everybody thinks the sky's above them. Well, fact check, mostly false, because 55% of the sky is actually below you. Some of the sky is above you, but only about 45% of it. Of course, you could get slightly different numbers depending on your assumptions. I just rounded the Earth's radius to 4,000 miles, and I regarded the edge of the sky as the edge of the exosphere, which gave us a pretty big volume of sky. But whatever your exact specific numerical assumptions are, these are the calculations you would have to use to figure out the relevant numbers. Anyway, I hope you thought that was fun. I sure did. Let me know in the comments if you have any questions, and be sure to subscribe for more of the swankiest math videos on the internet.
I'm unstable, feeling hard to keep the cable cut and unsort the table. If Texas Instruments don't reply, I think this time it might be fatal. Wish to sell my own fake, cause I'm jaded.
Hate the odds that I calculated.
Press and pull and pray and push it all the way through the whole blue
Planet faded.
psychosomatic habits, why you so